Oh, shoot.
We're live already.
We are live, everybody. I did not anticipate that. Well, yeah. We can leave this for a moment. Sorry.
Okay, everyone saw me using my e-cig. I did not intend them to see that.
All right, everyone. Well, we started sooner than we anticipated. We'll hang out here for a few moments.
So have we got anyone doing a short presentation before we start, or I can't remember exactly what we decided, if it was between Rainer's presentation and mine.
Cameron, I think you're muted.
Yeah.
Oh, shit. Thank you. I was going to do a quick little thing about Mount St. Helens.
Yeah.
It's the 40th anniversary of Mount St. Helens. Okay, so we'll chill here for a few minutes. People can log in. We haven't, even though we've started the stream, the event has not started, everyone, so welcome. You can look at our dazzling faces for the next 4 minutes until we actually start. I'm gonna get my drink.
Hello.
Yeah, hello, everybody. Hello.
Hi, everyone.
Hello.
Grab a drink, join us.
Yeah, you can see we're coming from apparently 4 very different locations in the universe. Very exciting. And I think we all took our own photos. I think this is true. Back before the quarantine, I was on the moon, took this nice photo of Earth.
Yeah.
All right. Yeah, so welcome everyone to our event. This is the Astronomy on Tap, the Los Angeles chapter of Astronomy on Tap. We've had to move online in light of the COVID pandemic, but we're still trying to bring these events to all of you. So welcome. If this is your first time, the schedule for tonight is we will have 2 separate 15-minute-ish talks on different types of astronomy. So first we'll start out with Dr. Virginie Faramaz, who will be talking about exoplanets, planets orbiting around other stars being detected by radio telescopes and radio waves. And then we'll take a few questions from the audience through the YouTube Live interface. And then our next speaker, Dr. Rainier Janssen, will be speaking about the hidden universe and how we detect the hidden universe using a variety of different telescopes, also kind of radio based. And then we'll take some questions for that. And then my co-MC, Dr. Kaylin Henderson, and I will be leading Astronomy on Tap, astronomically themed pub trivia for all of you. And we have an interactive way, a new interactive way for you all to participate through the Poll Everywhere website, so you can interact and see what other people are answering and what we're answering and what the correct answer is. And hopefully it's a little experimental, but it should still be fun. And yeah, and because this is Astronomy on Tap, we're going to be consuming beverages of our choice. So we hope that you will be as well. And what are you guys all drinking this evening?
Yeah, Virginie, what do you have?
I have started with a vermouth that comes from Chambéry, which is the city where I'm coming from my Savoy in France. And after that, I will switch to a pisco because Chile is in my heart too. I spent 3 years there and I'm going to talk about the facility that is in Chile. So seemed appropriate.
That's exciting. We're doing a tour of the universe and a tour of the world for drinks.
Yeah,
yeah, I didn't know you were from Chamonix, Virginie.
From Chambéry? You didn't know?
Chamonix or Chamonix?
No, Chambéry.
Oh, okay, my mistake.
But not far.
Not far. Yeah, it is Savoie. Okay.
Yeah.
And Rainier, what are you consuming?
I'm consuming something that completely disappears in my screen, apparently.
It seems appropriate given that your talk is the hidden universe.
It's a Dutch favorite. It's called gemeentepils.
Gemeentebus.
Yes.
Dare I ask what that translates to?
Pils is like pils, pilsner, and gemeente is like municipality.
Ah, okay. Okay. I like it. I didn't know you were going to be drinking dark matter. It's very exciting.
Yeah.
Hey, what are you drinking?
Yeah, so I don't know if this is going to show up. Oh, you can't see my glass.
Oh, you're also drinking dark matter.
So this glass has constellations on it. It's probably tough to tell, but so I am a huge fan of very peaty, very smoky Scotch. So what you can't see,
Oh my God.
a bottle of I've got some Lagavulin 16, and then as the night progresses and things go a little more off the rails, I've got a flask with unknown whiskey. I don't remember what I put in there the last time that I drank from it. So I think tonight's gonna be a lot of fun.
Okay, so I didn't announce, but many of you, I think you guys all know this, and many of our viewers may as well. So today, to the day, is the 40th anniversary of the eruption of Mount St. Helens, a volcano in the Cascade Range in the Pacific Northwest, close to where I grew up. And yeah, it's the biggest volcano eruption in US history, and it was a really big deal, and it happened 40 years ago today. So when I was digging through my parents' house several years ago, I found this strange object in the garage, and it turns out that Jim Beam, the whiskey maker, decided to commemorate this event 40 years ago by making a special aged whiskey in this really strange bottle shaped like Mount St. Helens, and it includes like ash from it, and it's very strange. So I found it. Evidently, my parents bought it, and now I don't think I have the wherewithal to wait another 10 years for the 50th anniversary. So I'm gonna drink this tonight. It smells like whiskey. So this will be, I don't think I'll be drinking all of this tonight, but I will be drinking some of this tonight. So that's my beverage for this evening. Oh yeah, so in light of that, I just, for people not familiar with Mount St. Helens and the eruption, I made a cool little slideshow that I really wanted to really quickly show. Let's see if I can do this.
Plus, you've got a T-shirt that says volcanic something.
Oh, yeah.
Oh yeah, you've got the T-shirt. What?
There was a trail race that runs around it every September that I participated in a few years ago, and it runs on a trail that circumnavigates the mountain. So I figured it was the only appropriate thing to wear tonight. Let's see if I can share this screen. Okay, can you guys see this?
Yeah.
Okay, so this is what Mount St. Helens looked like before the eruption. So 40 years and 1 day ago. And then over a few short minutes on the morning of May 18th, 1980, it had the largest landslide in recorded history, where it lost 1,300 feet of the top of the mountain, just collapsed and then blew off the entire north face and filled the sky with ash, and left. Ash basically covered everything. It was dark during midday. Ash covered vehicles. I know.
Jeez.
And what you're left with, this is looking into the crater, because it didn't just blow off the top, it blew off the northern face, so you can basically see into the crater. And the cool thing is, so there was a scientist like us, although dealing with probably more pressing matters than what we deal with, and he worked with the U.S. Geological Survey. His name was David Johnston, and he he was staffing and monitoring with seismographs the earthquakes that were happening somewhat frequently on the near the mountain. He was a few miles from the summit of the mountain. And his last words that are recorded were him radioing in to the nearest town where the base of USGS was at the time, Vancouver, which is where I'm from. And his last words were, "Vancouver, Vancouver, this is it." And then presumably he was annihilated by the blast wave of the volcano as it erupted. But so I'd like to dedicate a cheers to David Johnston and his service to science and keeping us all safe. So
Cheers.
Cheers.
Cheers. How was the first sip, Cameron?
it's pretty good considering. So Jim Beam says that it ages for 100 months. And then I guess I aged it for another 40 years. So, yeah, it's pretty good. Anyway, let's get started. Enough mucking around here. So Virginie, you'll start us off. Kaylin, would you like to? I'll go mute and stop my video. Same with you, Rainer. And
I start sharing my screen.
yeah, and Kaylin, would you like to introduce Virginie?
Yeah, I would love to. So hello, everyone. Again, I hope you have your drinks at the ready and your brains turned on or off. You know, quarantine is strange. It is my extreme pleasure to introduce the first of two fantastic speakers tonight. So with us to talk about exoplanets is Virginie Faramaz, a good friend and colleague. She's a postdoc up at JPL, and she studies how planets dynamically interact with asteroid belts and comet belts. So you can kind of think of it like a big, great orbital dynamics pool game that's just constantly happening in your head. She's also asked me to mention that you may hear some non-human sounds in the background. No, it is not a prisoner. It is her cat, who goes by Jasmine, or who actually usually goes by Bratty MacBrat. That's the Dr. Bratty MacBrat, I believe, to us. So yes, please don't call PETA on us. And without any further ado, thank you, Virginie, and take it away.
Thank you very much for introducing me. Hi, everyone. It's a real pleasure to be here and to talk to you about my research. It's been a while since I wanted to do that and finally got the chance. So I've been told just have fun and just talk to people just like you would be to taxi drivers, strangers at the airport, and this is what I'm gonna do. So basically what I do is I hunt planets with radio telescopes. So what does it mean? So usually if you're a little bit familiar with the way scientists hunt planets, you may have heard about, I just talk about three techniques. Callan might be a little bit disappointed that I don't talk about the one he's studying. I'm sorry. But the main ones are, so radial velocity. Oops, sorry. So radial velocity. So basically when you have a planet going around the star, and of course the animation, yeah, the animation goes. So when you have a planet orbiting around the star, it would make the star wobble a little bit. And when it wobbles and when it recedes from you, its light would turn a little bit red. And when it comes towards you, it will turn a little bit blue. And this is how you know there's a planet around it. This is how the first exoplanet was discovered back in 1995. There's another technique that is called transit. So basically you have a planet passing in front of the star. And if you monitor the light of your star, when the planet passes in front of it, you will see a dip in the light of the star. Now, as you may guess, these two techniques that are relatively biased towards planets that have short orbital periods, because you need to monitor the star for quite a bit of time to take a look at the wobble or either the transit, which is super cool because this is the way we're actually spotting Earth-like planets in the habitable zone and looking for Earth analogs. This is super cool. But that's not all there is. And people like me are also interested in planets that are further out, beyond those short period planets. And these are also super interesting. I hope you will be convinced about that. And to spot them, there is another technique that is called direct imaging. So you actually take an actual picture of your planet. The problem is that your star is just like super luminous, and when you take a picture of it, you have all these little speckles in the image, and there are numerous techniques of post-processing or masking the light of the star so that you can see your little planet appear. And currently this technique works quite well, but you need your planets to be relatively young, massive, and very bright. And it's super interesting to spot these planets that are at large distance from their star because they do interact with debris disks. So debris disks are like asteroid or comet belts. I'm more focused on comet belts, and it's super interesting. These planets are super interesting because when they interact with debris disks, they can send those comets inside the system on Earth-like planets where they will deliver water, organics, everything that you need to build life. And this is why we're super interested in spotting those, because this helps us marking the X on the treasure map and where to look at for Earth analogs that might have developed life. So here in front of you have an artistic view of a debris disk. And I remember when I started working in that field like about 10 years ago, and I was looking for this sort of images, there was none on Google Images. I was typing debris disk because there was no result. And now I have the choice between, I don't know, dozens of images, which makes me super happy. We're making a good job at advertising these. And I really like that one because it shows a couple of interesting things. So first of all, you can see that there's a planet there that is very close to the comet belt and presumably shaping the inner edge of it. You can see that you have bodies of the size of comets, which sometimes collide among themselves. So it's not like your typical science fiction movie collision-like where everything is just like colliding all the time and it's total panic. It's not like that. But these collisions happen and they will produce smaller bodies and also dust. And because these debris disks are made of a multitude of smaller bodies, they are much easily imaged than a single planet. Okay, a single dot versus a multitude of little dots. And here I'm going to show you some examples of that. Haha. So planets, because they can interact with this disk, they can shape them. They can give them like really exquisite shapes. On the right here, you have images that have been taken very recently with the sphere instrument. You can see spirals, you can see shadows. This is really beautiful. And the other images were all taken with Hubble. You have Beta Pictoris here, which is seen edge on. So it's like a slice. And you can see that there is something going on in here. You have discs like look like, we actually call that one the moth because it actually looks like a moth. This one here, I hope you guys all see my cursor, but so on the bottom right, there is this one which has spirals in it. It might not be clear because yeah, there's dust all over the place. And here is Fomalhaut. So Fomalhaut, here you have a ring. So of course, if you see a debris disk and it has a perfect circular shape and you see it completely face on, you will see a circle. But chances are you will not see your disk exactly face on and you will see it with some inclination. And so the projection makes that you see an ellipse. But some of these disks are actually not perfect circles. Some of these disks are actually ellipses. And so how do we know that? Well, because you can see here on the disk of Fomalhaut, if I take the center of the ellipse that I see with the disk, it's not, it does not coincide with the star. The star is not at the center of the ellipse. This actually tells me that this ring is an actual ellipse. And this kind of thing does not happen by magic. You have to have planets. So you can see any one of these disks as some sort of a crime scene. And then my job is to play CSI in space and just profile the culprit and who did that. This is how we hunt planet using debris disks. So now all these images, what they have in common is that they are made with reflected light, visible light. So let me take you through an example, something that I have published a few months ago, actually. So this is a debris disk that is seen with Hubble. So Hubble sees visible light. And visible light is actually reflected by small dust grains. Remember, in your debris disk, you have dust because of collisions, you have all sizes of dust. And so the visible light is reflected by tiny, tiny grains that are a few microns in size. This is the size of bacteria, basically. And they reflect this visible light, and we make these images. The thing is, have you ever seen like dust dancing in the light, you know, in a ray of light? Just imagine that, but in space, and you have these dust grains. They're very sensitive to the light of their star, which tends to blow them away, and they're all over the place. If I just use again the CSI analogy, it's like having a footprint, but it's been raining in the meantime, so everything is a little bit smeared. And if I want to profile my planet and I need accurate measurements of the geometry of this debris disk, which I don't really have here. So the idea is like, okay, I'm going to take a look at bigger grains because they are not blown away by the star like that, and they are not all over the place. And if I want to see bigger grains, then I need to take a look at infrared light. So infrared light is thermal light. It's the equivalent of putting on the thermal goggles, you know, like in action movies when they want to spot the villain in a building and they put on the thermal vision and they take a look at where the villain is because of his thermal signature. This is exactly what we do here. We're taking a look at bigger grains, putting on the infrared goggles, and this is with the Herschel Space Telescope. So now you're going to tell me, yeah, but Virginie, this looks really like shit. I mean, you said that you wanted to measure the geometry of your disk and take a look at bigger grains, and look, it looks like basically blobs. So, okay, yes, it does. Because the resolution and the level of details at which you can see an image will depend on the wavelength and also on the diameter of your telescope. So basically with Herschel, we're taking a look at grains that are 100 times bigger than those seen with Hubble. So 100 times bigger is about the size of your hair. But the thing is that if you want the same level of detail as with Hubble, you need a mirror to compensate for the loss of detail. You need a mirror 100 times bigger, which means a mirror about 100 feet of diameter, which is huge, and we don't do that. So what are we going to do? This is where we use AMA. So this is a picture of me in front of AMA. We're at 5,000 meters of altitude. So I'm very much freezing here. You can see I'm in my scarf, in my hat, but I swear it's me. And I'm very much oxygen deprived. I was actually wearing an oxygen bottle and tubes in my nose, and I removed those to make the picture. The reason is that we place these observatories at a very high altitude. If there's less oxygen, it's normal. It's because the atmosphere is thinner. And usually when we want to take a look at infrared wavelength or AMA wavelength, we have to go where the atmosphere is thin, because otherwise it blocks the radiation. So this is why we have these observatories at that kind of altitude. And with AMA, we're going to see even bigger grains than Herschel. We're going to take a look at grains that are about 10 times greater than Herschel. That would be, we have left the infrared domain of wavelength, and it's not radio wavelength. The advantage of radio wavelength is that when you want to collect this light with a telescope, you don't need a surface that is as precise as a mirror. You can have a metallic surface. It's enough to collect the light, which is really cool because then it's much cheaper to build an antenna than an actual telescope with a mirror. And so you can build plenty of those. But now if you have followed what I was saying, I'm telling you right now that we're taking a look at wavelengths 10 times greater than Herschel. So you would be able to tell me, Virginie, what are you talking about? If you want the same level of details that you were seeing with Hubble, you would now need an antenna 8,000 feet in diameter. And obviously your antennas here, the one you show us in the picture, they're not 8,000 feet of diameter. So what is this? What are you talking about? Well, there's a secret behind AMA, and it's called interferometry. So, so far I've talked to you about lots of things that I've talked with strangers, and what comes next is an exclusivity for Astronomy. I've never tried to explain that to general audience. So I hope you understand. If you don't, just leave comments. That would be great. I'm all up for constructive criticism. So what is interferometry? Well, okay. The principle of interferometry is the following. If you have a pair of antenna and you separate them from 1 kilometer and you recombine their signal, it is the equivalent of an antenna of 1 kilometer of diameter. You get the same level of detail, the same resolution. The thing is that you don't exactly get an image. So let me get you through how that works. You have a pair of antennas. Hey, we're a pair of antennas and we're separated by 1 kilometer, so we can see that level of details. We can see things that big in the sky. So right now, we see that portion in the sky. Is there something that big in the sky here? Yes, no. And then the Earth rotates a little bit, so they have a slightly different point of view. Do we see something that big here? Yes, no. And you repeat that for your pair of antenna. You combine that with all the pairs of antenna. ALMA is 66 antenna over the field, and you can separate them. You can have different separation on them. So you end up with the kind of a map of a yes, no, is there something big there? And then you can totally reprocess that with computers, and you end up with this kind of image. Voila, le débris disc. So this is the debris disk that we're trying to see with bigger grains. You can see now that grains are not all over the place. I can measure the geometry, where this ring starts, where it finishes, with exquisite precision. You can see that the center of the ellipse here with the white diamond does not coincide with the star, which actually tells us there is a planet acting on this disk, and that this disk is actually not a perfect circle. And then I can set the profile of the planet. So this is how we hunt planet with radio telescopes. And now we'll just to finish, I will show you a gallery of different things that we can get. So an ALMA gallery. So right in the middle, it's not exactly a debris disk, it's rather a protoplanetary disk, which means that planets are still likely forming in there. There's still lots of gas. The thing is that ALMA can peer through this gas to see where the dust is, where are the solids that will allow to form planets. And this is really, really cool. On the top left, you have a fomalhaut, which I showed you in scattered light at the beginning of the slideshow, was still the star that is not exactly at the center of the ellipse. As you can see, you don't have little grains scattered all over the place. This is super well defined. Here on the top right, I love that one. I'm actually currently working on that one. In that case, we don't even see a disk in reflected light. We only see it at infrared wavelength, and with that level of precision, we see it with ALMA. This is a debris disk that surrounds it's the only system so far where we have 4 planets that have been directly imaged. And we took pictures of the debris disk with my colleague Mark Booth, and I have another paper in preparation with other observation, and we actually have hints that the outermost planet B cannot carve the inner edge, and so we must have another hidden planet in there. Here, I also like very much the example on the bottom left with my colleague Seba Marino. We found this disk and we saw, oh, there's a gap in there. Okay, so to carve a gap that wide, we need a planet that big. But if we have a planet that big, it would totally empty the gap. But the thing is that there is still something in the gap. It's not exactly empty. So instead of having one big planet, we likely have rather two smaller planets. It's just like there's not just one culprit, but there's an accomplice, okay? There are two of those doing it. And finally, there's this image of Beta Pictoris. Beta Pictoris is the first debris disk that was ever imaged. One of the things you can do with ALMA is you can actually take a look at carbon monoxide gas, which is the kind of gas that is released when comets collide with one another. And you can see that there is this big clump here that tells us where comets collide. This was the first system for which exocomets were detected. And these were actually detected before the first exoplanet was ever discovered. It was back in '89. And they were watching the star and seeing that there were metal lines in the star that were variable. And they thought, oh, for us to have that, we have to have exocomets falling onto the star. And I think the community was not ready yet. The first planet had not been discovered. And so they were kind of booed in conferences, and they were told nasty things such as, oh, you see aluminum in your star, you're sure this is not a giant garbage bin falling onto your star? This kind of nasty things. But yeah, exocomets were discovered before the actual first exoplanet, and this was with Beta Pictoris. So I hope you like this talk. I will take any question, and if you don't want to hear the question, you can just look at these beautiful images I made in the Atacama Desert where ALMA is. Thank you very much.
Hey, let's cheers to Virginie. And I looked this up while you were talking. I think, as they say in France, à votre santé.
À ta santé. À ta santé.
Excellent talk. That was really great. Let me get some whiskey.
Thank you.
That was excellent. Good job, Virginie.
Thanks.
Anybody who has any questions, feel free to write them in the YouTube chat window. I think we got one already. Somebody, Mary Parker, was asking, this is a Fourier transform. And I think she might have been referring to the UV diagram.
Yes, absolutely.
About that.
Yes, it's a Fourier transform. I didn't go into such details as to explain what is a Fourier transform because it is a broad audience. So I hope the yes/no map analogy was okay-ish. but yeah, actually, this is totally a Fourier transform.
Okay, thanks for answering that. Again, people feel free to write questions in the chat. I will use my powers as MC. You might have co-MC, sorry, Cameron. You might have said this in the talk, I can't remember. Have you been up to the Atacama Desert or up to
Yes.
Alma? How did the altitude feel? What kind of effects did that have?
You're deprived of oxygen. So basically you don't see yourself, you don't feel yourself, how do you say that? I've lost the word. You tend to fall asleep because of the lack of oxygen. You're slightly drifting into passing out, but you don't really feel it. So there are doctors up there who will monitor you very closely. And so we're having this oxygen. So we were taking oxygen all the way up. And once we were up, we were having this oxygen bottle on our back with tubes that were going into our noses to have our oxygen supply. Yeah, it felt really weird. We had one member of the crew who left the oxygen for like 15, 20 minutes and he was already dozing off. So yeah.
Wow.
Yeah.
I've been up to the summit of Mauna Kea, which I think is the highest, but that's not quite, I think it's a couple of thousand feet shorter.
I've been there. I've been there too, and I can totally compare. And Alma is worth. It's worse. It's worth, And it's worse.
Yeah, I remember looking at a chart one time that said how much of the oxygen in the atmosphere are you above at various mountain summits throughout the world. I can't remember, everybody jump in if I'm wrong. I want to say you were above maybe 30% at the altitude of Alma. So maybe in the neighborhood of tens of percent, but it is very much significant, as you attest.
Yeah, exactly. And when you arrive there, you go first to San Pedro, which is a village that is just already 2 kilometers of altitude high, and you can already feel it. And then you're going like 5,000 meters for Alma. It's really crazy.
We have a couple more questions, so I hope I'm pronouncing this right. Gaur May, were the first exocomets discovered around Beta Pictoris?
Absolutely.
Absolutely. Straight from the source.
Absolutely. These were paper by team from Paris, led by Alfred Vidal-Majar and Marie Lagrange, who did the observation. And I actually know about the whole story because my PhD advisor, Hervé Bust, was part of the team, and he was doing all the dynamics behind it. Yeah.
Ah, that's fantastic.
So 1989, 1990.
Okay, okay. We've got another one from, again, apologies with the names. I'm sure the whiskey will help. From Omar Sadek. Can the radio method be used to search for potential Dyson spheres around distant stars?
I would have no idea.
Yeah, that's a good question. I do not
know your limits. Know your limits, and no, I don't. I have absolutely no idea.
So just so everybody's clear on what a Dyson sphere is a science fiction idea where advanced civilizations would be able to construct a sphere surrounding an entire star to collect all the radiation that's output by that star. So yeah, that's very good.
Except if it were a star.
That's not a star. That's a
yeah.
And so yeah, presumably if we're able to detect the presence of planets due to interferometry and such, one would be able to, maybe, I don't know.
I don't know. I mean, the way the work I do is basically an indirect method where I take a look at the thermal light that is emitted by grains of dust. I know that some planets, because of the magnetic field, you can have some synchrotron emission that would emit radio wavelengths too. So it's not, strictly speaking, impossible to detect them directly, although I guess we would need telescope with sensitivities largely exceeding the current capabilities that we have. Now the whole question is a Dyson sphere emitting any kind of radio emission? If yes, why not? But if not,
it probably depends on how big they made the sphere, and if it's on the size of your how do you call it, planetary system, and it's a sphere which is, like our Earth or so, it has a temperature, then actually ALMA would be the perfect instrument to see it, right? Because it's imaging dust at few tenths of kelvins or even less.
Possibly. Yeah, possibly, because so we will have bigger. So the dust grains I see are like a few tens of AUs from their host star, but and they're millimeter size with ALMA. But if you take a look at the body that is bigger, but which is closer to the star, possibly there is some kind of soft spot where the thermal emission would be visible by ALMA. Then it's a matter of sensitivity and resolution, I guess.
Yeah.
Do we know in this, let's say, hypothetical Dyson sphere situation, how many stellar radii would the Dyson sphere be? Is there a generalized formula?
I have
like an innermost or outermost stable Dyson sphere, depending on your stellar structure chart? We have another question, so we'll end on one more. What I'm going to take, again, entirely seriously questions. This is from Astro on Tap longtime attendee Brian Federa. Have we discovered llamas orbiting any stars outside of the solar system? I can only assume he's hearkening to Bertrand Russell's
the image that you showed that Was it a llama or an alpaca or what was
These
in
are vicuñas.
vicuñas? That's right.
These are vicuñas. I took all these pictures myself, and the ones with the llamas. So of course they're not orbiting stars, but they are very common in the Atacama Desert. And the pictures you have here, I was lucky enough to go to the geysers del Tatio, and we had a guide who was making us do the tour backwards so that we just avoided the crowd, and he took us like off the path for tourists. And because there was no one anymore, the vicuñas came out with the babies, and it was so beautiful.
Oh, that's really cute. Well, let's give Virginie Faramaz, guest speaker tonight, #1, a round of applause. We'll give it to you.
Thank you very much.
Very much,
I really was looking forward to do that, and I'm super happy.
Yeah, thank you sharing on a Monday night.
Cheers.
All right. How's everyone doing? I've consumed too quickly too much of this this fine aged St. Helens. Whoa.
I'm almost done with my martini. I should switch to the pisco now to honor Chile.
Yeah.
I say hello. If any Chilean is watching us, I say hola.
When you did not mention inarguably the greatest exoplanet detection technique of gravitational microlensing.
Absolute microlensing.
Finished my drink, but I had more scotch, so I'm doing great.
All right, so I guess we'll move on to our next talk from Rainier. I will introduce our speaker. So yeah, I'll be the MC for this portion. Kaylin and Virginie, do you guys want to slowly hide away? Dr. Rainier Janssen is a postdoctoral fellow at the NASA Jet Propulsion Laboratory. He spends most of his time in the lab working on the development of new cameras and spectrometers for far infrared telescopes. If he does find a moment of spare time, he studies the coevolution between supermassive black holes and their host galaxies. And in his free time, Rainier enjoys hiking and playing board games. The former is somewhat difficult in the current times. The latter is a lot easier, as shown by the fact that he's averaging about 1 game per day since the start of the lockdown. That is impressive to be able to keep that up. So, so I'll let you take it away. Thanks.
Yeah, thanks, Cameron. Thank you for inviting me. I'm excited to be here and to talk to you about basically the motivation of why, when I'm actually not locked down at home, spending so much time in the lab developing new techniques for the far infrared. And the motivation for that is basically to observe a universe which is hidden from our eyes and which we can see if we look a bit more close at the image which I had on my background, which is this lovely galaxy called the New Galaxy Catalog, object number 6240. It's a galaxy, as you can see, and there's a lot of starlight coming. But one of the most prominent features is actually, if you look in this Hubble Space Telescope image, are these dark clouds, which you see all across the galaxy, blocking our view from probably a lot of starlight. What is happening here is, if we relate back to Virginie's talk, this is actually all gas and dust. Gas and dust now not on a planetary scale, but on a galactic scale. And this gas and dust is scattering a lot of the light, not towards us, as in the protoplanetary disks, but away from us. So we basically see a backlit dust. And in order to get around the dust, we need to go, actually this dust is something we see in our own galaxy as well. So this is a picture I took last year in Grand Teton National Park, where we can actually see the Milky Way over here. And again, we see these strange dark clouds, which are dust and gas, which is absorbing the starlight coming towards us. So instead of a lot of stars in our Milky Way, we're actually seeing sort of backlit black clouds. Now, going back to our galaxy image, luckily there's something we can do to look around the gas and dust, or actually look through it. Because while our eyes and and the Hubble Space Telescope are limited to visible wavelengths, we can build telescopes which look in the infrared. For example, the recently decommissioned Spitzer Space Telescope. And when we now add in red the infrared emission, we see that we actually see this infrared emission coming from all the regions where these black clouds are. So these black clouds are hiding stars, which we can see in the infrared. And more prominently, we can now actually see the nucleus. So hidden here in the center of the galaxy, we can see very bright nuclei. And if we zoom in on that with our even higher resolution telescopes, we can actually see here in the inset in the corner that we see there not one, not two, but actually 3 nuclei. And we think actually that each of these nuclei is harboring a supermassive black hole, which is about 1 billion solar masses in weight. 2 of these are very active, and as a result of their accretion, their X-ray light is illuminating the gas around it, creating highly ionized light, which is highlighted here in green. So we have 3 nuclei. We have all these tidal tails. This is actually a galaxy which recently merged. So actually 2 or maybe even 3 galaxies which recently collided, merging into a single galaxy. And as a result of all this turbulence, this galaxy is actually forming stars at a rate of about 150 solar masses per year, which is 50 times more than our Milky Way. So these galaxies, which are obscured by gas and dust, are actually very interesting. And now you say, okay, we still see light, right? Why do we bother in different wavelengths? Well, let's take a look at the Hubble Space Telescope, one of its deepest images, the Hubble Ultra Deep Field. And we ask ALMA, which can see all this gas and dust, which is heated by all the absorbed radiation. And we ask it to look at some places in the Ultra Deep Field where there's a lot of infrared emission coming from. And I'll zoom this out for you, because here we see a number of galaxies which ALMA observes in gas and dust. And all these galaxies actually don't have an optical counterpart. There's so much gas and dust in these, what we call luminous infrared or ultraluminous infrared galaxies, that all the starlight, all the light from the accreting black hole is absorbed by the gas and dust, which warms the gas and dust, and that re-radiates the emission, which we can see with ALMA, but no visible light. So we actually now have 2 populations of galaxies, the ones we can see and the ones which are hidden from view by all the gas and dust. And there are many of those, as this image from the Herschel Space Observatory actually shows. So this Hubble image shows that we have many of these galaxies. Each of these dots is a galaxy forming hundreds, if not thousands, of solar masses of new stars every year. And we really need to see far infrared to see these galaxies, because as I said, they're not there in the visible. So we now can take images, but of course the universe isn't flat. And we actually want to see if we can make this 2D image from both the visible and the invisible or the hidden universe into a 3D image, like this simulation from the Eagle project. What we can see here in 3D, which how we anticipate the universe to look like, is like all these filaments. All the dark matter has collapsed. All the dark matter shown here in blue has collapsed into structure, which are these filaments or these nodes. And in these locations where there's a lot of dark matter, the gravitational pull will pull in the gas and galaxies will start forming. And all these galaxies are here in orange, red, and yellow colors. So for example, this would be a galaxy cluster, and here would be slightly more lonely galaxies. So how do we go from a 2D image to not a simulated, but an observed 3D image? For that, we need the distance. How far is each of these dots away from us? And there we can actually rely on pioneering work done here by Edwin Hubble while he was at Caltech using the Wilson Observatory here in Pasadena. And he discovered that galaxies, they have a correlation between their distance and how quickly they are moving away from us. Now, this is an effect which we now know is the effect of our universe expanding. And because of our universe expanding, if a galaxy is 1 million light years away, it is actually moving away from us at a speed of 50,000 miles per hour. And in addition, if something is a million light years away, the name already says it, light would take 1 million years to get to us. So when we look out into a galaxy, we actually see a correlation between the time, so the age of the universe, or the look at what it was, or our look back time, the distance at which it is, and the velocity, so how quickly it's moving away from us. And we can use this relation, so we can measure velocity very easily, and using Hubble's law, we can then derive distance. So how do we measure velocity? Well, you can think of this as an ambulance. When an ambulance or a fire truck moves past, you hear the tone of the sirens change. And when it's moving away, the tone changes to a lower note, which means the wavelength, so the color of the light, so the wavelength is longer, which in terms of light means it becomes redder. And we can see exactly that effect happening in this graph. So here we have taken a spectrum of a galaxy. So a spectrum is basically, we take the light and we split it into very small pieces of wavelength. We can do this, for example, with a prism. So basically, if we would measure a rainbow, for example, how much of every color of light is coming from our rainbow, we've made a spectrum. Now, if we do that in a very high detail, we see this for a galaxy. And we see some very prominent features. For example, this sort of spike here is one of the lines created by ionized or by hydrogen. And what we see if the galaxy is further away from us, and as a result moving away from us, this line actually shifts into the longer wavelength, or the redder part of the spectrum. We know always from experiments on Earth, we know where this line should be, so we can calculate back how much it has shifted, and as a result, how much redshift, as we call it, this galaxy has. Hence, we can calculate how much speed it has, how much velocity, and then we can calculate from that the distance and which age of the universe it was at. Now we can do this in the optical, and a very big survey, which has done a lot of galaxies like this, just observed spectra of a lot of galaxies and gotten their redshift, gotten their velocity, and gotten their distance, is the Sloan Digital Sky Survey. It's done hundreds of thousands of galaxies, and it actually has constructed an image like this. So the distance from the center, we're here at the center, Milky Way is here. We see all the galaxies as they are the distance from us, and then in the circle around, this is where they're on the horizon. And we can actually see the same web-like structure with dense regions and empty voids as we have seen in the simulation. So we can do this for the optical universe. But can we do it for the hidden universe, where about half of all the light that's coming from stars and galaxies has been absorbed by dust and is now coming through us in the far infrared? Can we do it there? Yeah, we can. We just need spectral lines. And so here's a typical spectrum for what we call a luminous infrared galaxy, a galaxy very similar to what we think to, for example, NGC 6240. And a galaxy like that has this enormous bump in the infrared, which actually are wavelengths of about 1 millimeter in length. And this bump is the dust, the thermal emission of the dust. But on top of that, we see all these spikes. And these spikes are the emission lines, predominantly from carbon monoxide or ionized carbon. And if we can find these lines and compare that to where we expect them to be, we can determine the redshift. So these spikes actually move from redshift 1, half the age of the universe, all the way to redshift 10, and they're here, which is about 500 million years after the Big Bang. So one instrument, going back to ALMA, which Virginie very nicely introduced, ALMA can do this very well. It's an extremely sensitive instrument, and it actually has detected the second most distant spectroscopically confirmed galaxy in the universe. So it's seen this line, and we know that this tiny blob is actually at a redshift of 9.11, which is about 5 million years after the Big Bang. And more surprisingly, this line is actually ionized oxygen. Now, the downside of doing this with ALMA is that ALMA can only see about this much wavelength in one go. It has a very small spectral bandwidth. And the downside of this, if this galaxy had been in a slightly different redshift, we would have to retune ALMA. So we look here, we see nothing. At some point you have to say, maybe it's a different redshift. So you move over one band. Also not there. Move over another band. Also not there. Move over another band. And while getting a line, if you know where it is extremely efficient with ALMA. ALMA is a very powerful telescope to do that. Finding where that line is initially is can be very time consuming. So we want something which is doing a large spectral band in one go. We can make instruments like that. And for example, this is Z-Spec, which used to be on the Caltech Submillimeter Observatory, which is located on Hawaii. It had a very wide spectral bandwidth. So this is a spectrum taken with Z-Spec of a nearby galaxy. Again, we see the CO lines. And for comparison, well, Z-Spec can do this in one go. These green lines is what ALMA can do in one go. So ALMA would need to retune and retune and retune many times to get the same spectral information. And while it takes longer, a single tuning of ALMA can get the spectrum much quicker than a single observation of Z-Spec. Getting the full spectrum becomes already much more comparable. The downside of something like Z-Spec is that it's only observing a small part of the sky. It's basically observing a slit, a line, which we can place over one or maybe a few galaxies at a time. And the second thing which is problematic is it's big. The problem is a prism can be of the order of a raindrop. Raindrops are breaking the light into what we see as basically a spectrum. But as the wavelength becomes 1,000 times longer to go to these millimeter waves, also every component which breaks light needs to become 1,000 times stronger. So these instruments are typically the size of a meter and need to be cooled to almost absolute zero. Otherwise, we have too much light from the instrument itself in the infrared. So my main work is actually how can we make this instrument which can do a lot of galaxies at the same time. And for that, we need to shrink it. And using techniques, basically superconducting techniques, we can actually shrink this instrument down to something, a silicon computer-like chip, a penny for reference, which can do the same functionality, but now on a 20 square millimeter silicon chip. And we were actually planning to take this spectrometer called SuperSpec to the Large Millimeter Telescope in Mexico. And if everything had gone to plan, I would not be here sitting in Pasadena. I would actually be in Mexico, hopefully showing the first light on the spectrometer. But we actually have high hopes that it will work because about a year ago, no, actually a year and a half ago, a team from my alma mater, the Delft University of Technology, as well as their Japanese collaborators, they brought a very similar chip, their picture inspired by ours, to Chile. Next to the ALMA telescope is a smaller telescope called ASTE. It's basically a single dish of ALMA. And they observed with a similar technology, the galaxy IC 1623. And they show they can do a full spectrum. They can see the CO line, determine the redshift of this galaxy. And for comparison again, how much ALMA would have been able to do. Now I've included a QR code for a nice movie they made about their first light deployment. And if it's allowed by Caltech standards to advocate other research, I'll ask Cameron to put a link up in the description of this video as well.
Of course, we can do that, no problem. With that joyful note of that, we are ready to go to the telescope with our instrument, and we hopefully can get similar or even better results than my alma mater. I would like to, having convinced hopefully that this is the way to go from this nice 2D image from the Herschel Observatory to a future 3D image, I will leave you there and take any questions. Excellent. Thank you very much. Oh, my green screen is messing up here. Yeah, that was great. Thank you.
Thanks.
Woo!
Thanks.
I like how you got in another Alma reference when you referred to your alma mater.
I hadn't even taken that one in.
All right, so we had several questions from the audience on our YouTube live. I encourage people who have more questions for Rainier based on his talk to include them in the YouTube live stream question comment box, excuse me, on the side, and we will try and address them here. So let's see. One question was, what's the difference between a quasar and just a regular black hole?
So basically the difference is that a quasar is a supermassive black hole which is eating. Basically, when you put stuff close to a black hole, it starts accreting, and the way it does that, it forms like a planet or like a star with a planetary system forming. It forms something very similar, a supermassive black hole with what we call an accretion disk, and that accretion disk becomes very hot and becomes as a result very luminous. And these very luminous accreting black holes are what we call quasars.
Excellent. There was an additional question relative to when you mentioned the observable universe. There was kind of a tongue-in-cheek question asking how many galaxies are in the unobservable universe. But I figured I'd ask that to you anyway, so we could talk a little bit about cosmology and so on and so forth.
So I don't know if anyone ever dares to put numbers on how many galaxies we see.
I think it's on the order of the number of galaxies that we've detected using Sloan and other large-scale surveys is on the order of 100 billion.
Yeah, that was my mental thing is 10 to the 10 stars per galaxy and 10 to the 10 galaxies in the universe. So yeah, that's about right. So one of the tricky things, and one of the things why you really need to do this, observe this far infrared universe, is that the only thing we really know for certain is how much light is coming from them. So we see that about half the light in the universe produced by stars, produced by AGN or quasars, is absorbed by the dust and comes towards us in the far infrared. But one of the big uncertainties is actually, if we go to redshift 2, we know reasonably well how these galaxies look, but we actually don't know beyond redshift 2, so about a third of the age of the universe and earlier, we actually don't know much about how many galaxies in the dust obscured universe there is, and as a result, we actually don't have a good handle on that. And it's a really interesting question because there's different models which tell us maybe we have dust obscured galaxies to the very first or very early in the universe. As soon as we have carbon produced by the first star, we have dust. But maybe dust forms a lot later, and we have these dust obscured galaxies only much later. So that's a very open question, and I wouldn't dare to put numbers on the relative number of galaxies between visible and dust obscured.
So I study exoplanets, so I will happily put a number. If half of the light is absorbed and obscured by dust of the light that we would have detected, and if we're not detecting all of the light that's emitted by the unobservable universe, that's probably another factor of 2. So it's probably 1/4. So it's maybe like a few galaxies that are unobserved.
Yeah, maybe.
Well, I even thought that I interpreted the question totally differently. I thought it was like, what's beyond the observable edge of the universe? Which of course is because it's unobservable, we don't know. But that's driven by the finite speed of light and the finite age of the universe, why we can't see that. So the answer to that is we don't know. It could be infinite, but it could also be finite and large or small. I don't know. Are there any? Oh, there was another a quick question. Does the technique that you were describing and the research that you were describing enable millimeter wave spectroscopy on CubeSats or any other small satellites?
That really depends on how small we can get our cryocoolers. The downside of using superconductivity is that we need to cool it to something of the order of a fraction of a Kelvin, so a fraction of a degree above absolute zero. And we can do that, but a typical cooler is the size of a human. So actually, the superspec cryostat is about, I would squeeze a bit, but I would fit inside.
So that means you're the size of an average human, roughly.
Yeah, the size of an average human. And so if we can get that down, yeah, then maybe. But that would require a lot of engineering to get our cryogenics small.
So the main constraint is an engineering task in reducing the size of a cryostat.
Yeah, and I don't know if there's a feasibility limit to that engineering task.
I see. I see. Okay. All right. Yeah, thank you very much. That was awesome. Yeah, applause and cheers. And yeah, so now I think it's time for Astronomy on Tap pub trivia.
Pub trivia. So I hope everybody's at least 2 sheets to the wind. We're going to try some experimental stuff. We're playing stuff off the new album. We're going to really hit it. So we're going to try something that is not something we can really do in the pub setting. So we're trying to take advantage a little bit of the virtual environment here. And I'm going to go ahead and share a screen. Let's see if this works. Everybody bear with for a hot second. We're going to try to make the trivia questions a little bit more interactive. All right, so does everybody see this?
Yes.
This first slide? So what we're going to do, for those of you out there watching at home, if next to your YouTube Live browser tab, if you could open up another browser tab and go to the URL that's down at the bottom here, pollev.com/AOTLA. So this is for Astronomy on Tap LA. There, what should happen, and you don't have to create an account, you don't have to log in, this is none of that. This just brings you to a portal website that will allow you to answer questions as we go from question to question, and we're going to try to show the actual results live as we're going through here and doing the actual pub trivia. So I'll give everybody kind of another 30 seconds or so. If you could bring up a tab. Oh, it looks like people already answered.
Not the end of the world if you aren't able to go there. Like if you're on your phone and you can't keep the live stream going while going to another website, that's okay. You can still enter your answers into the YouTube Live chat. But this is an additional way in which we can have some sort of interactivity. And we'll bring up the questions, and you can like see what other people are answering, and then see what you're answering, and see it's great.
So I'm gonna jump ahead. I've already activated the first question, and people are answering. So the first question is: dust grains that reflect starlight are the size of which of the following? So we made this one multiple choice. Kind of start off with the softball. Those of you who are really paying attention, this was maybe mentioned in Virginie's talk. So the options here are human hair, proton, penny, or a bacterium. So penny, as in the coin, just to be clear, and proton, in case it really matters, we're taking the length scale to be the charge radius. And we'll give people a couple seconds here. This, an interesting thing to think about as you're answering this, whether or not you know the answer, is what do you think the dynamic range of these options is? You know, how much larger is the largest option compared to the smallest option? I'll admit that when I was writing this question and doing a little bit of research, I actually didn't really know the answer. So I think when we go through this, it'll be kind of cool. So we've got human hair is winning, coming in close-ish second. We've got bacterium. Got a few out there for proton. Got some hangers on for pennies.
I like penny.
Give everybody
a penny. Big fan.
Big fan. We'll give everybody maybe 10 or 15 more seconds, kind of chime in. And this is a single human hair, so it's not, you know, a human.
It's not like grabbing a tuft of scalp.
Yeah. This is an individual strand. All right, it looks like it's kind of basically settled. So we've got human hairs taking about 50% of it, bacterium about 10% behind, and then proton and penny are roughly tied. So what we're going to try here is in flipping between the questions with the live results, we've actually tried to put images and movies as jumping off points. Brian Federa, I'm looking at you. You've been asking us to do this for a while. All it took was a pandemic. Okay, so here are our options. We're going to go from smallest to largest. So for a proton, here just a kind of a classical idea of an atom. Proton is about 0.84 times 10 to the minus 10 microns. So that's pretty tiny. Then we have a bacterium, an individual bacterium. Kind of depends on which bacterium we're talking about, but it's a few microns. Then this is a scanning electron microscope image, I think taken by the University of Maryland, of a single human hair. Kind of looks, anyway, looks not like what I expected. It's about 100 microns. And then a penny is about 20,000 microns, a little bit under. It's about 3/4 of an inch wide. And so, drum roll please, the winner is actually a bacterium. So yeah, Virginie mentioned this, that
I mentioned both the human hair and the bacterium, but yeah.
Okay.
The human hair was for the infrared.
So we'll give full credit to anybody who said bacterium or human hair.
My penny answer fell short.
All right, so now let's go ahead. I'm going to activate the second question. So Comet Swan, see if this is working, was recently discovered by an amateur astronomer using data from what spacecraft? So Comet Swan, and our options are Spitzer Space Telescope. We had a Spitzer celebration a couple months ago, before the shadow days. It's operated out of the IPAC Science Center here in Pasadena, or Nasadena, as we call it. There's also the Hubble Space Telescope, which recently celebrated a big birthday milestone. There's the Solar and Heliospheric Observatory, or SOHO. There's the Transiting Exoplanet Survey Satellite, also known as TESS. This was recently launched a couple years ago. And then there's the Chandra X-ray Observatory, which along with Hubble and Spitzer, those are 3 of the 4 of NASA's great observatories. So it seems like SOHO, a lot of people are liking SOHO. Chandra's coming in. Number 2, Spitzer and Hubble, neck and neck. TESS, where's the love for TESS? So much exoplanet science, but yet.
Yeah, but maybe not Comet Swan science.
Okay, so SOHO's pulling ahead here. Pulling ahead.
Also, I have to be honest that the first time I heard about TESS was basically when I moved to JPL. I've never heard about TESS before that, so.
Interesting. Yeah, it's a relatively new mission, especially compared to the 5 that are listed here. Certainly in the exoplanet community, it's very well known, but it's probably not quite as well known as Kepler outside of the exoplanet community. All right, SOHO is really running away with it. It's about half the votes, and
good reason.
Roughly tied. All right, we'll give everybody another 10 seconds, maybe. Probably no late charges. All right, we'll go ahead and call it. So the answer, drum roll please, is the Solar and Heliospheric Observatory. And so this is actual data. Comet data is so cool. Things in astronomy are very far away, but solar systems are close. And so this is Comet Swan. This was taken, what's today? The 18th. This was taken not even 3 weeks ago. Got this from skyandtelescope.org. And here you can actually see, if you look really closely, it's kind of like you can actually see the time-dependent motion in the tail of Comet Swan.
That's pretty awesome.
Right? How cool is that?
Yeah.
All right, let me get the next one ready.
All right, next question.
Question number 3. Sorry again that the things are getting cut off. Today is the 40th anniversary of the catastrophic eruption of Mount St. Helens. Beyond the Earth, What 3 solar system objects have confirmed active volcanoes? So again, today marks the 40th anniversary of the catastrophic eruption of Mount St. Helens. Beyond the Earth, what 3 solar system objects have confirmed active volcanoes? So Cameron was giving a big shout out earlier.
Oh yeah, well, I'm a big fan of Mount St. Helens, so.
All right, this one is a little bit different. We're doing a word cloud. And so some people have seen that you can actually answer more than once. So, there's 3 answers. You could guess even more than 3 times. And if you see a little bit of a lag in the answers, I'm vetting them so that nobody writes butts.
Butts.
Or poop. Or wildly inappropriate words. This is an outreach event.
Oh, so this is pretty good though. Some good ones.
Yeah, what have we got? I'm clicking away. What do you see?
So there's the big ones that people have been answering are Io, Venus, Europa, Enceladus. Ooh, there's a probably in there.
Oh, somebody wrote probably.
Mercury, Mars. So, yeah, so there are only 4 objects in the solar system that we have actually witnessed volcanism occurring on. Yes, we've seen there's a lot of planetary objects that have a history of volcanism. So for instance, the moon, we don't see active volcanoes blowing up and stuff, but we do see that there are lava tubes. We do see lava fields, all the Maria, the darker regions on the surface of the moon, like the Sea of Tranquility, the Sea of Serenity, the Ocean of Storms. These are all darker areas that were formed by basalt flows from earlier, like 3 billion years ago, or several 100 million years ago, when the Earth was younger and it was still cooling from interior dissipation of heat. But
so it looks like the answers are kind of settling down, they're converging.
yeah, it looks like Io, Venus, Europa, Enceladus, Mars are kind of.
And I hope, I'm a few drams of whiskey in, so I hope I didn't let anything inappropriate in there.
Oh no.
But here we've got a lot of options, a lot of answers. Thank you everybody for giving it a shot. We've got a couple. We've got Io with the period and an Io. We've got Venus with the period and Venus. Those count as the same. That's all right.
So the correct answer, even though there have been a number of different systems that have shown past evidence of volcanism, the 3 other systems other than the Earth that show active volcanism are Io.
Nice work, everybody.
Io. So Io is one of the moons around Jupiter. It's one of the Galilean moons. It's really close to Jupiter. So when it orbits around Jupiter, so all of these systems, like on the Earth, we have volcanism from tectonic plates shifting around and subduction zones and welling up of mantle and material from the interior of our planet, kind of poking its way out into the surface and erupting. But tectonic plates only really occur on Earth of all the objects in the solar system. But on Io, we get volcanism because Io is so close to Jupiter that its gravitational field, the gravitational field of Jupiter is tugging it and pulling it and squishing it and moving it around so much that it's essentially like pushing material out. Oh, I had a ball here I was going to demonstrate that with, but forget it. It's warping it around enough, and it's forcing material out. That material is mostly like sulfur volcanoes, as opposed to the typical stuff, the mantle-based volcanoes that we have here. The other 2 systems are Enceladus.
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 Eliza.
Enceladus is a moon around Saturn.
Enceladus.
And Triton. You aren't going to sing Triton?
And we've got some images too. Thank you, Cameron, for the cool science. So we can actually show you some data.
Oh yeah, so these are
one of them
cool cryovolcanoes. These are ices being forced out of crevasses on the surface of Enceladus. Enceladus is an icy moon that surrounds, or that's orbiting. Oh wow, I'm fading out here. Okay.
You're part of the hidden universe.
The Matrix. Holy cow. Okay, I'm gonna stop that. That's freaking me out. So Enceladus is has an icy surface, and there's a subsurface water source, and it's forcing out through these crevasses on the surface, and flinging icy watery material in, up hundreds of miles into the atmosphere, and it's actually feeding it's creating one of the rings around Saturn, the E ring, which is made up of small icy ice crystals and such that are coming off the surface of Enceladus. Do you have, is this the?
Yeah, I put them all in. Let's get.
Oh yeah, so this is
So this is
Io.
actual data. This blew my mind when
Yeah.
Cameron showed me this image.
Oh,
Yeah, so you can
This is
see on the left side near the edge of Io, you can see the material that's being kicked off hundreds of miles off the surface of Io, and that's like essentially sulfur, ash, and lava that's being spewed out of the interior of the moon. It's
Yeah,
crazy.
and when I looked this up, I think it was by the taken during the 9th orbit of the Galileo spacecraft as it was orbiting Jupiter, the planet that hosts the moon Io. And it was taken, I think on June 28th, 1987, somewhere around there.
Mhm.
97, 87. And it was taken from about 370,000 miles up. So just to give some kind of distance scale.
And there's two volcanoes erupting in this image. The one obviously on the left side near the edge of the planet, but also straight right in the middle. You can see kind of a circle. Yeah, right there. And to the right of it, you can see the shadow that's being cast by the light that's traveling through that cloud that's directly on. You can see the shadow just to the right. It's
Which is super cool because you can see that the light source illumination direction, is to the left, let's
it's
say.
on the left.
Yeah.
Yeah.
Yeah, that's very cool.
Yeah.
So we went from black and white to this color composite image from Galileo, and we'll end on this one.
Oh yeah.
Actual.
This is just like a 6-frame movie that was taken by several images taken by. Is this also Galileo? Or is it-
I don't know. I don't know. It's a good question.
Do I recall correctly that the actual active volcanism on Io was like predicted, I don't know, a few days, weeks before it was actually
Oh,
observed?
really? I don't know. That's
That's
possible.
cool. That's cool.
I don't know.
I think I recall that.
So I did my PhD at Ohio State. So let's do a little shout out. IO.
Okay. All right.
I mean, this is really just the gift that keeps on giving. All right, next question. All right. So hopefully everybody is saying last month, this is another multiple choice, astronomers reported evidence for an intermediate mass black hole in a distant galaxy. In this context, what does intermediate mass mean? So one more time, we've got last month, astronomers reported evidence for an intermediate mass black hole in a distant galaxy. In this context, what does intermediate mass mean? So right now, mass of the sun and 1,000 times the mass of the sun, kind of neck and neck. Oh, not so neck and neck. Nobody believes that the Earth is intermediate mass. Oh, somebody does!
Oh, I will believe it.
Jupiter, no love for Jupiter? We were just talking about Jupiter? Okay. A lot of people are thinking that it's the high end of the mass scale here. We did everybody, a solid and ordered the answers in order of mass, just in case.
Nobody likes Jupiter.
Nobody likes Jupiter. They've had enough Jupiter talk after all that. Volcanism. Okay, Earth's getting a little love. Sun's getting a little less love.
Shall we just reveal so we don't?
Yeah, I think this one is settled. Nobody gets poll numbers of 80%.
Okay.
All right, and the answer, drum roll please, 1,000 times the mass of the sun.
Yeah, it's pretty interesting. So everyone's familiar with supermassive black holes, right? Because those were in the news when we had the Event Horizon Telescope that was taking images of a black hole that was primarily taking the image of a black hole around the Virgo cluster. Was it Virgo or Coma? I think it was Virgo. I think it was M87. So that black hole was like a billion or a couple billion times the mass of the sun. So it's called a supermassive black hole. And we think that all galaxies host a supermassive black hole in their centers. And then we know of other mass black holes primarily created by when stars, massive enough stars, go supernova, and what's left behind is a stellar mass black hole. So these are on the order of 1 times the mass of the sun, or a few times the mass of the sun, or maybe 10 times the mass of the sun. But up until recently, we haven't really had any evidence for intermediate mass black holes being on the order of 100 or 1,000 or 10,000 masses, solar masses in mass. It's just hard to see them because, as Rainier talked about, you only really see black holes when they're actively absorbing material, and you get something called the tidal disruption event, where essentially you rip apart a star, or material feeds down onto that black hole, and it gets really, really hot, and it starts to glow, and you can see that stuff because it's a black hole, right? The black hole itself isn't emitting light. It's just the stuff around it.
Yeah, and so people are maybe wondering kind of exactly what we're looking at. This is in the direction of the constellation Aquarius. The actual black hole itself is not the fuzzy blob in the center, though you can see the trace of the galaxy. It's the object that's inside the white circle. And so this is data taken with the Hubble Space Telescope relatively recently. But actually, the first indication that there might have been something going on that might have hinted that there was an intermediate black hole, or at least something going bump in the night, were data taken by NASA's Chandra X-ray Observatory. We talked about it a little bit earlier. It's one of the NASA's four great observatories. And the European Space Agency's X-ray multi-mission, XMM. And that's actually how it gets this kind of gross, what we call a phone number, the name up here. So XMM is the name of the mission to first identify it. And then this J and a bunch of numbers are the coordinates. Right ascension and declination, or you can think of it as longitude and latitude kind of projected onto the sky. And so that this tells you what discovered it and where is it. And you kind of have a lot that you need to know to go look for it. All right, everybody ready for the next question? Let's do it. Let me get
Lay it on us.
So we have, in her 1925 doctoral thesis, Cecilia Payne, later Payne-Gaposchkin, proposed that stars were primarily composed of what? 2 elements. So again, we have, in her 1925 doctoral thesis, Cecilia Payne, later Payne-Gaposchkin, proposed that stars were primarily composed of what 2 elements? All right, all right. So we've got some hydrogen, we've got some helium, oxygen, a lot of good answers here. And the story behind this, we'll go into it a little. I'm glad that the answers are still coming in. Astro on tap, Nastadina, you never fail to amuse me.
So 1925 and a woman in astronomy, is she part of those women who didn't get the chance to have their work recognized, or was she
that is a good
well treated in the field?
That is a good question. I don't know off the top of my head. I know that a lot of her work, unobtainium, we're going to let that one through, wasn't really fully recognized kind of for its brilliance until there's a biography, I think, that came out, I don't know, within the past few years that really detailed her life. Yeah, I do not know at the time how much credit she was really given, or if it was another, DNA debacle. All right, let's see. We've got some other plutonium, uranium. Ooh, we got a lot of answers. This is good.
Hydrogen and helium are just like the bigger things.
Yeah, they seem to be the overwhelming.
But they're the obvious ones. So, I mean, I actually don't know the answer. This would be the astronomers' known answer because it's the main components of the universe. But I wouldn't be surprised if there's some curveball here.
Well,
Like
there
glitter and unobtainium. Those are my votes.
well,
I'm actually having someone on the YouTube feed who just answered my question and says that her IDs were rejected actually.
oh wow, okay, so maybe it really wasn't until recently that she really got the credit that she deserved. Speaking of credit that no one deserves, somebody wrote hydroxychloroquine. That is, spoiler alert, not the answer. Well, all right, let's get straight to it. Looks like the answers are kind of converging. So the correct answers, drum roll please, are hydrogen and helium.
Yeah, she was spot on.
Hydrogen and helium. So nice job. You know, we had a lot of answers, big range here, including diamonds, berkelium, glitter, unobtainium. But we got there. Humans. Who wrote humans? Okay. Oh, hold on. I'll cheers to that. So here's this is a picture of her while she was working on her doctoral thesis. So again, to just stress, this was her PhD work. She was the first person to pioneer what at the time seemed to be just a totally off the wall idea. So actually a lot of the astronomers, preeminent in the community in the entire Western world at least, thought that the elemental composition of the sun and of all stars was basically going to be the same as the Earth's crust, so that it was going to be very heavily weighted towards silicates, which, we might laugh now, almost 100 years later, thinking that, the temperatures and pressures and just based on the formation mechanisms for stars, that there would be silicates, dominating the composition. But that really wasn't known. At the time, and she was the first to suggest it, and turns out she was correct. So cheers.
Good job, Cecilia Payne.
Yeah.
Cecilia Payne. All right, we ready for the next one? This one, I'm excited what people are going to write for this one. So it is, what country will double its astronaut corps from 2 to 4 people following its May 2020 deadline for applications? So again, we have what country will double its astronaut corps from 2 to 4 people following a May 1st, 2020 deadline for applications? So for this one, it's the first time we've had this type of a question. You can write in a question or write in an answer. I think you should also be able to upvote other answers, maybe if it's yours only, or maybe if it's any answers. We're kind of experimenting here, so feel free. And one of the things that's, all right, we'll let that one through. One of the things that's a hint is that it's an astronaut corps that currently has only 2 astronauts. So a lot of these countries they're all good answers, but some of them, might already have more than 2 astronauts in their astronaut corps. We have a multilingual kind of answer going on here.
Ooh, Space Force.
I didn't know there's going to be a Space Force movie starring Steve Carell. I just learned that.
It's not even a movie. I think it's a Netflix original. I think it's a series.
Oh, a series. Okay.
Yeah.
So right now we've got Finland, then Space Force, and then Mauritius, India, CCP. All right, there's a couple more coming in.
How can the USSR, which is no longer a nation, continue to have a space agency?
Interesting. All right, there's I've seen a couple go by that have spelled the answer. AOT, you deliver. There was a Narnia that just floated by. I don't know if everybody's seeing that. Here, I'm going to start showing new and top answers. So some people, it looks like people are maybe Googling. The correct answer is coming through hot.
Someone suggested Czech Republic in the chat.
Ooh, Czech Republic. That's I like that guess. I like that guess a lot.
Someone suggested the United Arab Emirates in the chat.
Ooh, the UAE. That's another good one. All right, it looks like things are basically settling. So I hate to disappoint, it is not Space Force. It is, and we'll go to the answer page here. It is the United Arab Emirates. So these are the two current UAE astronauts, Sultan Al Nayadi on the left and Haza Al Mansouri on the right. And they had a call. I can't remember if it was late last year or earlier this year. And the deadline just passed. Actually, on the same day that GIF of Comet Swan was taken. And so they're gonna double from 2 to 4. So that's pretty cool. Pretty cool stuff.
And then, of course.
I didn't even realize that the UAE had a space agency. I didn't know they conducted any kind of events.
Oh yeah, I had no idea.
Let alone having a manned space agency, like a human space agency.
Right. Homework for the audience is to Google the UAE Space Agency. I don't really know anything about it except that.
Okay. Sweet.
All right, next question. Let's kick it off. Okay. Engineers, again, sorry for the cutoff. Engineers at Georgia Tech are developing technology to help future rovers avoid sand traps, which is ultimately what caused the demise of what Mars rover?
Oh.
So again, engineers at Georgia Tech are developing technology to help future rovers avoid sand traps, which is what ultimately caused the demise of which Mars rover? There's no trick question. These are all Mars rovers.
I think I've heard the story about that. I don't know if I'm entirely correct, but the story was that they needed to make the actual rover lighter, so they decided to drill holes in the wheels, and then just realized that it was a shitty idea because it was actually trapping a lot of sand and everything. So maybe it's related. I'm not entirely sure, but I've heard that.
Well, and at the one of the mock rovers that they have up at JPL's campus, you can actually, and it's 1-to-1 size, so it's 100% scale. You can actually see on the wheel that it is Morse code. I think it's
yes.
Morse code.
So, the name of the team that didn't have the right to actually promote themselves, but they just found a way to.
I think I remember the story as I think earlier Mars rover actually had JPL plainly written on it, and NASA didn't want that in their next Mars rover, so they actually wrote it in Morse code on the wheels. So it's printing JPL as it's moving along on Mars.
That's fascinating. So
I actually should know this answer because there's a team at JPL which actually I think contributed to this research, and there's a audience participation. So there will soon be a launch of basically a crowdsourced image recognition. So you can help look at old Mars old Mars data taken by current rovers and help identify what is rock, what is sand, what is a ridge you cannot climb.
This is so great. There are so many projects led by asking for help of the community.
Yeah, I think that's great.
That should be live soon.
Well, so Rainier, you said you should know this. What would your answer be?
I actually guessed opportunity.
I'm always confused between all of them. I should just put in place some kind of mnemonic to just remind myself which one is what.
So there were two that were launched around the same time. It was Spirit and Opportunity.
Mm-hmm.
Curiosity is still up there, and I believe it's still doing science. I don't think it's had any.
Curiosity is going strong. It's been about 9 years. It's going great.
So which one is the one which solar panel was covered of dust?
That was Opportunity.
We're expecting the end of wind season.
That was Opportunity, yeah.
So that presumably was covered in dust after a dust storm and never really cleared off, and so it basically the battery died.
Yeah, exactly.
But Spirit happened much sooner, much earlier. I don't know anything about Sojourner.
No, and me neither. I don't know too much about Sojourner. It garnered the most votes, but the answer is actually Spirit. So yeah, as we were mentioning, Opportunity got covered in dust. So Spirit and Opportunity, yeah, everybody's loving up Spirit.
Click on that one.
You know, ultimately the demise really, I guess, for Spirit and Opportunity was their solar panels were covered in some way, and so they weren't able to recharge. Opportunity, it was dust. Spirit, it went somewhere and got trapped in a sand trap, and you know, as everything was moving, Mars was rotating and orbiting. It was on the it went into the shadow of some sort of geologic feature that it was stuck in a sand trap on the side of, and it was in the shadow long enough that it couldn't recharge, and its batteries died. Yeah, all right, now Spirit. All right, we're moving on to this one.
Everybody's going crazy on.
I just wanted to get it to 42. That makes sense. All right, let's get the next one going. Oh, actually, sorry. Before we get to the next one, here's a really cool video. This is a mock-up of what the engineers at Georgia Tech have been working on. So this is, you know, actual.
That looks great.
And this is this is smaller than the rover would be, but this is it getting itself stuck in a box full of poppy seeds.
It's getting out pretty well.
There's this kind of like super wiggle, and the wheels are moving in.
So the wheels are actually kind of rotating laterally so that they can.
It's sort of swimming, right?
The axle is moving left to right, to be able to provide additional traction instead of just spinning the wheels in place.
Yeah, it's very cool. All right, let's get the next one. I already made it live, so maybe people are looking. So NASA has held official discussions with what actor regarding?
I can't wait to see the answers to that one.
We're coming through. Regarding filming a movie on the International Space Station. Oh gosh, we got a lot of good stuff coming down the pipes.
Tommy Fauci.
Yeah, it's going to be Tom Cruise, but it's going to be played by Anthony Fauci. All right, Brad Pitt, Tom Cruise, Jean-Claude Van Damme, the muscles from Brussels.
Maybe you should put up the new ones as well as the top ones.
Oh yeah, have I not done that? Sorry, that's a good point. Let me get the top ones.
So the sentence is actually, I think, a little bit confusing. Filming a movie, or maybe that's just me because I'm French and there's something that is escaping me because of grammar, but filming a movie on the International Space Station, that could possibly involve that the filming occurs in the International Space Station?
I believe
yes,
that the actor would be going to space in order.
No shit, really?
Yeah, that would be the idea.
Can they send someone we don't like and then throw him into space?
No, maybe some people have already given guesses. Oh, who wrote?
Okay, so I guess this is why people are answering Trump to that.
I figured it was why people were answering Kaylin Henderson to that.
Yeah, people.
Cameron, someone answered Cameron Hummels.
Oh no!
Yeah.
Throw him into space.
Well, Cameron doesn't have as many votes as Kaylin, which I note is interesting. Which I will note. All right, so we got a lot of big name actors here, you know, and a lot of the top ones here are variations on Tom Cruise, except for one of them. Yeah, a lot of big names. We got Tom Cruise, we got Kaylin Henderson. You know, what do you do? The correct answer.
Yeah.
Oh, Tom Cruise, not Ted Cruz. I thought
Not
you were
Ted
Cruz.
Not Tom Cruise, not Tom Hanks, and not Kaylin Henderson.
Not Kaylin Henderson.
One thing I learned when I was looking this up is that apparently tickets for tourist visits up to the ISS, the International Space Station, aboard a SpaceX Crew Dragon spacecraft, are already being sold for $55 million. I don't know if there's launch dates attached. I don't know how anything is going, but I read that in the same article on the New York Times. So if anyone would like to make that Kaylin Henderson guess come true, just send $55 million to the following bank account.
That's a lot of money.
It's a lot of money. All right, we're getting through. We've got 2 more questions left. Let me get this one ready. Okay, question number 9. What is the name of the NASA mission whose goal is to test technology for altering the trajectory of an asteroid?
I would love to be part of that.
One more time, we've got, what is the name of the NASA mission whose goal is
I don't
to
even know the answer, but I'd love to be part of that.
for altering the trajectory?
I really like slam.
Kind of like Dart, like, you know.
Yeah, these are all great. I will have the
No,
audience
right.
know now that we're on to flask stage. Also, I figured out what's in the flask by taste. It's Talisker 12.
It looks like dark matter flash.
It kicks. But I'll let everybody in on a little secret. 3 of these are 100% made up by me about 4 hours ago.
Really interesting.
And
So
one of them is
Real
hopefully
acronym. One is the real acronym. The others are just BS acronyms.
totally, just totally garbage.
Oh,
I mean,
interesting.
they're
So
brilliant.
Dart, personally.
All right.
Did you also come up with what the acronym would stand for?
No, it took me too long thinking about whether or not I should capitalize which words and add letters.
You
Oh,
know that there
oh,
are sites that actually allows you to just make up your acronym. You just enter some keywords and it makes it up for you.
Really? That's amazing.
Yeah, actually, yeah.
So we'll go from ones that I'm least proud of to ones that I'm most proud of. Impact, I thought was pretty good.
That's pretty good.
No capitalizations. And I had to make sure to not use a word that I was using in the actual question. Now everybody loves impact. Impact is incorrect.
I prefer slam, the
I
underdog.
love Dart.
Second from the bottom is redirect. I made both both the E's, which are vowels. That is not correct. Then the last incorrect answer is slam, the double M.
I don't believe that one.
The correct answer is DART for the double asteroid redirection test. So
Okay.
the name is maybe a little confusing. It's not that it, now it's getting
Yeah,
good.
there's a big push on Dart.
Yeah. So the double asteroid, because the idea is that it will, they've already picked out, I forget the name. I wonder if I can find it real quick. But they've already identified, NASA has, which asteroid they want to go to. Let's see.
You have a video? Show us a video.
Show a video by popular demand. The video. Oh, Didymos. There it is. It's the host with the Didymost. And so here's a video showing the impact simulation. So I looked this up. 3 tons of TNT is what DART will slam into the asteroid with.
What the heck is going on? Are these isocontours, or is this just a bunch of crap? Why are we seeing concentric circles?
I leave this as an exercise to the Cameron to figure
I was already wondering if that would leave the trail of dust such that we would have a new meteor shower.
Yeah.
Oh, Virginie, that's an excellent question. So the interesting fact I was going to bring up is that actually it could. So the impact of DART onto the asteroid would produce the first meteor shower created by human cause.
That's really
Cool.
cool.
Something. So yeah, that's
They better not fuck this up and make chunks small enough.
Yeah, this could go either way. We'll see. So the launch date is expected in September 2022. We'll know. Well, who knows how everything right now is
Yeah, sure.
going to impact.
That's cool. Wait, so what's the technique? How is it actually, so it's impacting it in order to convey enough momentum onto the system to move it out of the, to move it?
Yeah, according to the New York Times article I'm currently reading, NASA plans to launch the 1,100-pound DART spacecraft. I think impact is September 2022. The launch date is expected in 2021. Didymos refers to the pair of asteroids.
Sure.
And DART is aiming for the smaller of the two, which is affectionately named the Diddy Moon. Oh, I love that. It's about 535 feet across, and the impact is expected to change Diddy Moon's orbit, 11.92 hour orbit by about 4 minutes. So this is big enough for telescopes on Earth to detect. And another thing I was wondering, it says that it's not high risk for any telecom satellites or any human-made space telescopes. I presume because a 530-foot object slammed into by 3 tons of TNT, the debris, won't be that big, and the probability of impact is also going to be small.
The probability of impact is small. Then what's the point of the whole?
No. The probability of impact of the space dust onto other human-made spacecraft.
Oh, I see.
Yeah. I hope DART isn't gonna just.
It just misses it. What's the whole point of the thing?
Well, come on, buzz the tower. All right.
So the whole. Sorry to
go.
to make this a little bit longer. The whole point of the thing is, this is going to strike this object and hopefully just change its trajectory and its orbit. But if it's like a rubble pile, like we think a lot of asteroids are, it might just obliterate it.
Yeah, and I wonder if the goal for this one, I don't actually know off the top of my head, or in skimming this New York Times article, is if it's to, I don't know what mass left over for Diddy Moon they expect, and what the resultant effect on the larger, more massive asteroid in the pair will be.
Huh, okay. Well,
yeah, interesting.
Something to set my calendar for. This is interesting.
Yeah, and this is the first test of really any sort of technology by humans to try to, figure out what we would do to save ourselves from some sort of extraterrestrial demise.
Yeah, but wouldn't it be like wiser to do that on something that would actually not cross the Earth path?
I don't think it will it?
Well, you could test it.
I mean, I'm taking a look at the video, and if you take a look, like the whole debris thing, this is the Earth path.
Yeah, I don't know if this
right?
video is accurate. These iso contours seem pretty large.
Yeah.
Like crossing the Earth's orbit. I think that's BS, but I don't know.
Yeah, you heard it from Drunk AOT. It's pretty
right.
Drunk
AOT won't.
Actually, people are starting to wonder on YouTube how many drinks I've had.
Oh, yeah. Well, how many?
I don't know, I don't know, 3.
Ooh, shout out to Christina Hulen for quoting Airplane. Guess I picked a bad week to stop sniffing glue. Brian Federa, what could possibly go wrong? I don't know. Let's just run it back, see what happens.
Yeah.
All right.
One last question, right?
Last one. And as longtime viewers of the program are well aware, it is a strong tradition to always have a Star Wars question.
Oh, Star Wars, yes.
Here
we go.
Those.
The arch villain, I'll say in quotes, maybe you identify with him. Emperor Palpatine originally hails from what temperate planet?
Ooh, a temperate planet.
Yeah, we've got
Wonder fiance. You know the answer to that question. I know it.
The arch villain Emperor Palpatine originally hails, not his newest hailing. Yeah, AOT, you guys are crushing as per usual.
Naboo, Wonder fiance says Naboo.
Oh, Kafefe, yes.
All right, let me get the new ones on there. All right. All right, Naboo, Kafefe. The leader is Kafefe. The real question is, audience, how drunk are you? How many drinks you drank?
Yeah, I would like to know, because they're asking me, at least someone asked me how many drinks I've had. So I would be curious on how many drinks they had.
Yeah.
That's the point. We would be in a bar if it weren't for this whole COVID situation. We will all be drinking, right?
Yeah, also, can we please stop typing Kofefe? I'm pretty sure those are the nuclear launch codes, and we're just letting everybody know. Yeah, we're not gonna need a dart. There's not gonna be. We're not gonna last another
How
year.
come there are like 15 Naboos?
Yeah, that's the thing I've noticed. It's like when someone puts in a new answer, instead of adding up to the others, sometimes it's just a brand new
It's like
one.
a problem with how Kaylin is doing this.
It's. I just think we need to shift gears and focus on hydroxychlorotoluene.
Someone wrote Tatooine instead of Tatooine.
Note in town. This is great. Ruprecht. I hope that's not a weird.
Oh, it's Ruprecht the monkey boy from Dirty Rotten Scoundrels. That's genius.
That's my bad for not recognizing that.
Good job, Ruprecht.
Exegol. That's a solid. Another solid. What is this? What's Moraband? Is that another? Is that a planet?
I think that's one of the people in the chat. That's one of our viewers.
All right. Looks like things are settling down.
Things are settling down. Kafefe's in the lead.
Kafefe's in the lead. However, drumroll please, the actual answer is Naboo. And again, even though people have been drinking, this is a time for everybody to be reminded that this is a family-friendly program, so we can end on, kids, this is what happens when you do drugs. Don't do
Naboo?
No, to Palpatine.
Oh, Emperor Palpatine? I don't think he was a rampant drug user. I mean, he was an arch villain of the series, but
he was sniffing the dark side of the Force, like
He's doing more than sniffing it.
I don't think Darth Sidious was actively taking amphetamines or anything like that.
I think that's up for debate. I think we should check Wikipedia.
Well, anyway. Yeah.
I'll stop sharing here. Thank you, everybody, for participating.
Thanks, everyone.
Leave comments, maybe, as to how you thought it went. We're trying out some kind of new technology from the.
Do you like the interactive website for answering the Astro themed pub trivia, or do you prefer it the way just with the interaction in the live stream comments?
Yeah, give us your candid feedback.
Yeah. Also, if you like this event, we have a number of events. We're doing this once a month. We're also doing our public lectures once a month, and you can look at our channel and see past events that we've done and recorded. We hope to continue that in the months coming up. In addition, we have partners. Tomorrow night, there's another Astronomy on Tap being led by University of Texas at Austin. So if you look up Astronomy on Tap, ATX, they will be having an event tomorrow night at 5:30 p.m. CST, so 5:30 PDT, and that should be super good. Columbia Astronomy is live streaming astronomy events with public lectures once a month. But in general, you can find out about other Astronomy on Tap events if you go to astronomyontap.org. That has all the events around the world. There are like 30 different chapters in different cities around the world, which of course, now a handful of them are doing streaming events on YouTube Live or Facebook Live or Zoom or what have you. But otherwise, they're just doing local events, and you can go to a bar and drink a beer and interact with astronomers and hear some science talks and get angry at Kaylin for ridiculous quiz questions and punch him in the nose, whatever. Something.
You may not do that. Decline. You may not do that. As the most famous CH on the program tonight.
I don't know if you're the most famous CH.
Well, I'm definitely top one.
Yeah.
Definitely top one. Is that still the Mount St. Helens?
Oh, it's still the Mount St. Helens. I think I'm halfway done with this wine beverage. Oh, it's fading. Just like it's like Back to the Future here. To oblivion. Anyway,
if we could get another virtual round of applause too for both of our speakers, Virginie Faramaz and Rainer Young.
Thank you.
Thank you.
Thank you, guests. Thank you very much for helping.
To do that.
Joining in for excellent explanations of the unknowns of space and now the knowns of space. And we'll see you guys. Caltech Astronomy has a public lecture in a couple of weeks. Stay tuned on our channel. And our next Astronomy on Tap is roughly in a month, also on our channel. So we plan to continue live streaming these because we're all stuck in our houses and drinking alcohol. So we'll see you next time. Thanks, everybody.
Ciao. Ciao.
Bye.
Be safe. Take care.